Welcome to another module in this massive open online course on probability and random variables for wireless communication. So in the previous module we started looking at Gaussian random variables and the various key properties of Gaussian random variables. One of the important properties of the Gaussian random variable we said is the following thing, that is, if I have L Gaussian random variables x1, x2, xl are Gaussian random variables with expected xi equals mu I, expected xi minus mu I, that is the mean of the Gaussian random variable I is mu I, the variance of the Gaussian random variable I is sigma I square, that is expected xi minus mu I square. Further, if I look at the covariance, that is we said if I look at the expected value of xi minus mu I times xj minus mu j, we said this is equal to the quantity sigma ij, and this we said is the covariance. Now we said if I generate a new random variable x, which is generated as a linear combination of these Gaussian random variables a1 x1 plus a2 x2 plus so on up to al xl. So this is a Gaussian random variable which is generated as a linear combination or a linear transformation, a linear combination of x1, x2 up to xl, then we said this x is in turn a Gaussian random variable. Very interestingly, the Gaussian random variable, which is generated as a linear combination of a group of random variables, is in turn a Gaussian random variable, and we also calculated the mean and variance of this new Gaussian random variable. So we said this x, the most important one of the key property is, we said x is, this is in turn a Gaussian random variable, and the mean and variance of x are given as n. This is the mean is summation ai mu I, and the variance is summation I summation j ai or summation I summation over I ai sigma I square plus summation over I summation over j not equal to I ai aj sigma ij. So this is the mean mu and this is the variance sigma square of this Gaussian random variable x, which is generated as the linear combination of x1, x2, xl using the weighting coefficients a1, a2 up to al. Let us now consider a special case of this linear combination. Let us consider a special case. So we are going to now consider a special case of this linear combination. So let us consider a special case of this linear combination where all the Gaussian random variables are 0 mean, that is mu I, that is expected xi equals mu I equals 0. That is all the Gaussian random variables that we are considering are 0. That is all the Gaussian random variables are 0 mean. Further, let us consider that all of them have identical variance, that is expected xi minus mu I square equals sigma I square, which is equal to sigma square. So this is the variance. All the Gaussian random variables have identical mean, and in fact the mean is identical equal to 0. So, all the Gaussian random variables x1, x2, xl are identical 0 mean Gaussian random variables, and further all the Gaussian random variables xi have variance, that is expected value of xi minus mu square is equal to sigma I square, which is equal to sigma square, that is the variance of all the Gaussian random variables is the variance of the variances of all the Gaussian random variables are equal to sigma square. So, these Gaussian random variables are basically identical Gaussian random variables. So, these are basically, see, because the mean and variances of these Gaussian, the means and the variances of these Gaussian random variables are identical. So, we say these Gaussian random variables are basically this mean, all the Gaussian random variables have 0 mean and all of them have variance sigma square. So, these are a bunch or a group of identical RVs, and further these are identical Gaussian RVs, identical Gaussian random, these are identical Gaussian random variables. Further, we are also going to assume that the covariance, that is expected value of xi minus mu I times xj minus mu j, since mu I and mu j are equal to 0, this reduces to expected value of xi times xj, which we are going to assume equal to 0. So, the covariance is basically equal to the covariance of any two Gaussian random variables, the covariance. So, we are going to assume that the covariance is equal to 0. Such random variables are known as uncorrelated random variables. When the covariance of two random variables is 0, they are known as uncorrelated random variables. So, we are assuming that all the random variables, Gaussian random variables are identical, and further they are uncorrelated. So, these two random variables, this implies that xi, so this implies that xi comma xj are uncorrelated. So, this implies that the random variables xi comma xj are uncorrelated, and specifically for the case of Gaussian random variables, uncorrelated also implies independence. This is not true for any random variable, but specifically for the Gaussian random variable, uncorrelated, the property of that is that they are uncorrelated implies that they are independent. And remember, this is not true for any random variables in general. This is only for the case of Gaussian. This implies for Gaussian and only for Gaussian, implies for Gaussian this implies independence. That is two Gaussian random variables are uncorrelated, then they are also independent. Therefore, x1, x2, xl, remember we are saying they are identical because they have 0 mean, all of them has 0 mean, that is mean of all of these Gaussian random variables is 0. All of these Gaussian random variables have identical variance sigma square. Further, they are all uncorrelated. Any two pair, if you take any pair of Gaussian random variables x1 and or xi and xj, they are uncorrelated, and we said specifically for the case of Gaussian random variables, since they are uncorrelated, it also implies that they are independent. Therefore, we are considering a group of L independent and identically distributed Gaussian random variables. So, we are considering group of x1, x2, xl in this context. In this scenario, x1, x2, xl are these are independent and independent, remember we have seen this nomenclature before, independent and identically distributed random variables. That is, each of these has mean 0, variance sigma square, and the covariance between these two, the covariance between any two Gaussian random variables is 0, which means they are uncorrelated, and since they are Gaussian, this also means they are independent. So, we are considering L independent identically distributed Gaussian random variables. Let us now again consider X, which is generated as a linear combination of these Gaussian random variables. So, similar to before, let us consider the new random variable X, which is generated as A1 x1 plus A2 x2 plus AL xl, which we can now write using vector operations as A1, A2 up to AL, x1, x2 up to xl, which I can write as, let me write this as the vector A bar transpose, this I can write as the vector x bar. So, this I can write this as A bar transpose x bar, where A bar is the vector A1, A2, AL, and x is the vector, or x bar rather is the vector, as we can see above, x1, x2, xl. So, I can write this as the vector. So, I can write this linear combination A1 x1, A2 x2 up to AL xl as the row vector A1, A2, AL times the column vector x1, x2, xl, which is basically A bar transpose x bar. This is the new random variable X, which we saw previously is Gaussian in nature. Now, what is the mean of this Gaussian random variable? The mean of this Gaussian random variable x expected value of x, which is equal to mu, which is equal to summation I ai of ai times mu I, but mu I, we are saying each mu I is equal to 0. So, this reduces to summation over I ai times 0, which is equal to 0. Therefore, mu is equal to 0. Since each of the Gaussian random variables xi has 0 mean, that is mu I equal to 0. So, for each random variable xi, summation ai mu I is summation ai times 0, which is 0. Therefore, the mean mu of the Gaussian random variable x is 0. Now, let us look at the variance. We have also derived an expression for the variance. The variance expected value of x minus mu square, and we have shown that mu is equal to 0 is equal to the expected value of x square, which is equal to summation over I sigma I square plus summation over I summation over j not equal to I ai ai aj sigma ij, and remember we said sigma ij this is equal to 0 because the covariance is equal to 0. Further, each sigma I square is equal to sigma square. Therefore, we have the variance, this is equal to sigma square. Therefore, we have the variance expected value of x minus mu square, which is equal to sigma square, which is equal to, as we are seeing above, summation of I ai square sigma square, which is equal to sigma square summation over I ai square, but summation over I ai square is nothing but the norm. So, summation over I ai square is a1 square plus a2 square up to al square, which is nothing but the norm square of the vector a bar. So, this is basically equal to sigma square norm of a bar whole square. Therefore, for IID Gaussian random variables, therefore, for IID Gaussian random variables x1, x2 up to xl, we have x which is defined as a bar transpose x bar, this is Gaussian. Further, x can now be represented as we have calculated the mean we have said is 0, the variance is sigma square norm of a bar square, where a bar is nothing but the weighting vector. Remember, we have defined a bar as the weighting vector a1, a2 up to al. So, what we have done is we have considered the special case, that is all the Gaussian random variables x1, x2 up to xl are 0 mean, they have identical variance sigma square. Further, they are uncorrelated, that is the covariance is sigma ij, the covariance is equal to 0. And for the Gaussian random variables, we said uncorrelated also means that these Gaussian random variables are independent. Therefore, we are considering a group of IID, that is independent identically distributed Gaussian random variables. And then we said, if we generate a new Gaussian random variable, if we consider a new random variable x, which is a weighted combination of these IID Gaussian random variables, that is a1 x1 plus a2 x2 so on up to al xl, then the mean of x is 0, that is x is 0 mean, and the variance is sigma square times norm of a bar square, that is sigma square times a1 square plus a2 square so on up to al square, and x is a Gaussian random variable in turn with this 0 mean and variance sigma square norm of a bar square. So, this is an interesting property which will in fact come very handy, which is in fact very useful when we analyze various communications, the behavior and the performance of various communication systems as well as wireless communication systems. So, we have seen a special case of the linear combination of a group of random variables. So, we will end this module here and proceed with other topics in subsequent modules. Thank you very much.